In this video, I want to remind you of the algebraic properties of exponents. I want to show you that those also work for exponential functions as well as for polynomials. The exponents kind of behave in the same way. And then I also want to show you the connection to the algebraic properties of logarithms. There are quite a few situations in pre-calculus and in calculus where the algebraic properties of logarithms allow us to enlarge the class of problems or the set of problems that we can solve, because these algebraic properties allow you to move things in an equation from one position to another position where other things might be possible. So let's just recall the properties of powers, properties of exponents in their normal position, and then show that those still work in the situation with exponential functions. So if I think about constructing a polynomial function or just a monomial function where I have x to some power, say I have x to the 6th power, all right? When we originally designed the exponent notation, we used it to track repeated multiplication. So x to the 6th power is the same as 6 copies of x all multiplied together. So if we think of that as the core definition for what we mean by these exponents, that it's repeated multiplication of the base, then by grouping these copies of x in different ways, by arranging them in different ways, we can deduce some of the properties of exponents. So here, what I've done is I've thought about x to the 6th, and I've unraveled it into 6 copies of x to the 1st power. All right? Now, the properties, the algebraic properties of exponents come from kind of regrouping it in different ways. So one of the first things that we have as a property of exponents is looking at multiplication of different copies of the same base to different powers. What do I mean by that? I mean x to the a times x to the b. So the base is the same, the powers might be different. If we think about what's happening with this kind of unraveling, this first guy, if I unravel it using this repeated multiplication idea, there are going to be a copies of that base x, and the second piece, there are going to be b copies of that base x. So if we just write this out kind of schematically, we have a bunch of x's all multiplied together. They're a times, or a copies of x here. And then x to the b, if we unravel that, maybe that's a little smaller. We've got b copies, or b times x right there. All right? Now, if we think about grouping those all together, that's going to be one of the properties of exponents, the kind of addition property of exponents. When I multiply two exponential terms, or two exponential expressions together, and they have the same base, the exponents add. So this is equal to x to the a plus b. This property extends and is usable with exponential functions as well as with polynomial functions. So if we reverse the roles of, say, a and x. So say I have an exponential function. Maybe I have 3 to the x power. That's an exponential function. And maybe I have 3 to the y power. So it's the same exponential function, but we're evaluating it, or we're different amounts of the 3s, different numbers of copies of the 3s going into that function. This property still works in exactly the same way. So 3 to the x times 3 to the y is going to be equal to 3 to the x plus y. Okay, so that's one of the first properties of exponents and exponential functions, this kind of addition property. And there's a second one. And this is going to be the situation when the exponents multiply. So here, we can think of it in the polynomial version first. So let's suppose I have x to the a squared. All right, so I've used some variables in here, and then I'm also thinking about a specific exponent too. So here I have a power raised to another power. Right, so we're kind of composing these powers. In this situation, if we unravel everything, the square tells me I have 2 copies of x to the a. X to the a times x to the a. All right? And using this addition property, this multiplication property for these exponents, x to the a times x to the a, that's got to be equal to x to the a plus a, okay? And from there, if I just simplify this expression, a plus a is equal to 2a. So I get x to the 2a. All right, so here we had a power raised to a power, and once we work through all these different variations, all these different representations of this, we end up with x to the 2a. There the powers have multiplied together. That's indicative of the pattern that happens in general. So if you have an exponential function, say I have 3 to the x raised to the y power, so there's two powers composing one another, or two exponents layered on top of one another, that's going to be equal to, if we think about systematically getting to the final result, you're going to unwrap this. You get 3 to the x times 3 to the x times 3 to the x. And there are y copies of this. All right? And then if we multiply those together using this addition rule for these exponents, I get 3 to the x plus x plus x. And now there are y copies of x in the exponent all added together. So finally, if we simplify that, we get 3 to the x times y, which is the same property that we had for exponents before. So if you're dealing with exponential functions or polynomial functions, the properties of the exponents themselves don't change. You can manipulate them and group them either when you have a multiplication of two exponential terms with the same base, the exponents will add. If you have a composition of different exponents, those exponents still multiply. Now I want to show you, just give you kind of an example of how these properties behave when you're dealing with logarithms. It turns out that the properties kind of are inverted in a certain way, or reversed. So here, think about it like this. The property of exponents that we're trying to exploit in both of these situations, what we're doing is moving the location of an operation. So here I have two exponential pieces, 3 to the x and 3 to the y, and I have multiplication between them. So the multiplication operation is at the level of the bases, okay? And when we move that into an operation in the exponents, it changes. We go from multiplication to addition in the exponent. Multiplication of the bases to addition in the exponent. For the second property, we have exponentiation of the bases, 3 to the x times 3 to the x times 3 to the x. Okay, so exponentiation of the bases turns out to be multiplication of the exponents. So these properties, if you think about moving the operation from something about the base to something about the exponent, it kind of downgrades the level of the arithmetic operation. We go from multiplication to addition, exponentiation to multiplication. What you'll see is when we look at logarithms, it does the reverse of that. It kind of downgrades the operation to move it in or out of the function. So let me kind of give you some examples and show you what I'm babbling about. First, let's remind ourselves what job an exponent or logarithm is supposed to do. So if I have an equation, a to the x is equal to b, this is equivalent to log base a of b is equal to x. Those are equivalent statements. And the way you get from one to the other is by applying a logarithm or acting with a logarithm on both sides of this equation. So the intermediate step to connect these, I do a log base a on the left side, and I do a log base a on the right side. Okay? And the logarithm base a is the inverse function to an exponent, an exponential function with a as the base. So those things cancel one another out. They unravel one another's operation and leave us with the x. Okay? All right, so this is the kind of logarithm operation. So the logarithm answers the question, what's the right power, base a, to get us to this result b? Okay, it's kind of an inverting question. And what I want to do to kind of make you aware of the properties of logarithms is I'm going to show you how some of these numbers have to be related for a very simple example. Okay. And the pattern that I show you, it's going to be specific to using base 2, but the ideas, the algebraic connections that we see with base 2 will apply to any other number. And maybe we'll do some examples to see that connection. So let's look at the following sequence of numbers. I can look at 2, which is equal to 2 to the 1 power. I can look at 2 squared, which is equal to 4. I can look at 2 cubed, which is equal to 8. And how about 2 to the 4th is equal to 16. All right. So here are a bunch of hopefully obviously true. Right, this is 2 to the 1 on the left-hand side, so it matches all the other patterns. Hopefully these are obviously true equations. 2 times 2 is 4, so 2 squared is equal to 4. 2 times 2 is 4, times another copy of 2 is 8, so hopefully that's true. If I multiply both sides by 2 again, I get 2 to the 4th is 16. So there's enough relationships here where we can start to explore the patterns that are involved. So let's take each one of these statements and convert it into an equivalent statement that involves a log base 2. So I want to apply the log base 2 on both sides and see what those equations tell me. So in this first case, if I take the logarithm of both sides, log base 2 of 2 to the 1 is equal to log base 2 of 2. Okay? And when we do that, we know that on the left-hand side, the base 2 and a log base 2 are going to cancel one another out as inverse functions. So a statement about logarithms for this first equation would be that 1 is equal to log base 2 of 2. If we do the same thing to the second statement, we can say that 2, that's the power, is equal to log base 2 of 4. From here, we can say that 3 is equal to log base 2 of 8. And from here, we can say that 4 is equal to log base 2 of 16. Okay? And what I'd like to do is I'd like to group these things in different ways to see if we can pull out some of the patterns. So if I take, for example, this equation, 2 is equal to log base 2 of 4. Right? And here I have 4 is equal to log base 2 of 16. So let's write an equation that we can use to mix and match the different logarithms that we have involved here and see if we can pull out any patterns from those. Okay? So what I've got in mind is maybe, how about 2 plus 2 is equal to 4. Right? So I've taken two numbers, I've added them together, I have a different result. Another thing that we might consider is that 1 plus 3 is equal to 4. Okay, so there are two equations, two different situations where we have two things on the left and one thing on the right, and each of those we can write in terms of a log base 2. Right? So what I want to do is I want to uncover, if I can, any connection between the arguments of the logarithms on the left and the arguments of the logarithms on the right. See what's there. So in this first situation, 2 plus 2 is equal to 4. We're going to use log base 2 of 4 plus log base 2 of 4 is equal to log base 2 of 16. Okay? Now that's a really complicated way of writing 2 plus 2 is equal to 4. And what we want to do from it is try to uncover some of the properties of this logarithm operation, this log base 2. To enforce the idea or to give us more material to work with, we'll do the same thing with this equation. It's a different way to add up to 4. So we have 1 is equal to log base 2 of 2. Log base 2 of 2 plus log base 2 of 8, right, is equal to 4. So that's log base 2 of 16. Okay, so now we have two different examples. And in those examples on the left-hand side, we're adding together two logarithms with the same base. And on the right-hand side, we have the result written in terms of one logarithm. So what I'd like you to do, really carefully, is to look at the connection, if you can find one, the connection between the arguments on the left and the argument on the right. Okay, you've got 4 and 4 and a 16 for this first example, and then you have a 2 and an 8 and a 16 in the second example. Can you connect those numbers in any way to come up with a conjecture about how the log might be behaving, what it might be doing in these situations? Okay? So think about that for just a minute. And hopefully, if you're just kind of mulling these things over and thinking about how they might connect, you might have thought about trying to combine the numbers on the left-hand side in some way to get the number on the right. And then you'd see an interesting pattern, because both of these examples seem to do the same thing. If I take 4 and 4, the arguments of these two pieces, and I multiply them together, I get 16. And you can check the same connection holds for this second example. I have 2 and I have 8. If I multiply those two numbers together, I get 16. Okay? So maybe we can combine logarithms if we have the same base. Maybe we can put them together by multiplying their arguments. So the conjecture that we have at this point is a possible property of logarithms. We've said maybe if I have log base, or let's say log base, make it some number c. If I have log base c of a plus log base c of b, so I'm trying to add together two logarithms that have the same base, right? Then based on just these two examples, we might think that the way to combine those would be with log base c of a times b. So this is a conjecture. Unless we can come up with a reason why we think that that actually works, we shouldn't be too willing to accept it just based on these two examples, right? If we think this works for all logarithms, as long as we have the same one, and all numbers a and b, we'd better come up with a way to justify that, a reason why it has to satisfy that pattern. So let's think about that, if we can come up with a reason why this must be true. Okay? So let's think back to the definition of the logarithm, what question it's answering. So this thing is the power of c needed to make b. Right? And this piece is the power of c needed to make a. And this is our conjecture. We think that adding those things together might be equal to the power of c needed to make a times b. So should these things be connected in this way? Let's double check. We don't necessarily know what these things are equal to, but maybe we can invent notation that will allow us to write this equation in a different way. So what do I mean by that? This log base c of b, that is equal to the power of c needed to make b. All right? So let's suppose that this thing is equal, just this one piece is equal to x, for example. And then maybe we can call this other guy log base c of a. Let's call that y. So we're introducing kind of notation to stand in for those things. And the reason is that I'd like to connect this back to the exponential version of these statements. So if I call this number x, right, if I say x is the power of c that's needed to make b, then all of that notation together means that c to the x is equal to b. Right? Does that make sense? I hope. And now, here on this side, we're saying the power of c needed to make a, we're calling that y. So if we raise c to the y power, that should be equal to a. So c to the y is equal to a. Okay? So now we've taken these kind of statements about logarithms, we've rewritten them in terms of exponent notation, even if we don't know exactly what those exponents are, because we're trying to come up with a general property, a general pattern that logarithms satisfy. Once we've said those two things are equal, then we can look at what's happening on the other side of this equation. This number is the power of c that's needed to make a times b. And here's the key. If we think about that in terms of the notation that we already have invented, we invented symbols for x and y for the values of these first two parameters, we can see if we can find this connection. Right? So the power of c needed to make a times b, I can figure out that power using the x and y notation that we invented on the left. We can make a times b by multiplying a and b together. That makes sense. But a and b are also equal to these powers of c. So the power of c that we need to make a times b, we can get that from c to the y times c to the x. That's just a times b written in terms of these powers of c. Okay, so once we have that property, that this is the number of c's that we need, we can now go back to the properties of exponents that we know to figure out if this number is actually equal to these two numbers. Right? So let's look at properties of exponents. C to the y times c to the x. I can write that as c to the x plus y, or y plus x. That's how we have it written over there, so let's use it over here. So that's equal to c to the y plus x. So the power of c needed to make a times b is y plus x. If we look at our left-hand side of the equation, we just said that this number is y and this number is x. So our equation, interpreted in terms of these exponents, is saying y plus x is equal to y plus x. And that's true. That's guaranteed to be true regardless of the c and regardless of the a and the b. This is a generic algebraic property of logarithms. You can use it whenever you want for any logarithm function and for any arguments, a and b. Okay? It can also be used in either direction. You can use this to combine two logarithms into a single term, or you can use it to split a logarithm into two smaller terms. Okay? So that's the first algebraic property of the logarithm function. And we've kind of uncovered it from a conjecture and then an argument that links it back to exponents. Right? From there, there's a second property of logarithms, which can be, we can argue that property just from what we already know. So if I think about this as a combining property, check this out. Let's suppose then, let's look at this. Suppose I have log base c of a times a. That's how I want to think about it. If I think about this as a times a, there are different ways that I might expand or manipulate this notation. Log of a times a if I want to use exponent notation inside the logarithm, can be written as log base c of a squared. Okay? But if I use this property of logarithms that we just proved, then I can split this up, and I can write this as log base c of a plus log base c of a. Okay? And that might not look that great until we notice that log base c of a is the same as log base c of a. So we can combine these like terms. We can say, if we compact this idea, that 2 times log base c of a is going to be equal to log base c of a squared. And now we have something a little bit more interesting. We have this idea that if there's an exponent inside the logarithm, we might be able to remove that exponent or transform it into a coefficient in front. And this turns out to be a really, really useful property for manipulating equations where you have funny expressions in the exponent. Okay? So this is a specific example. We looked at just a times a. But by using this property multiple times in different configurations, you can generalize this so that if you have any power, a to the n, inside a logarithm, you can move that exponent inside the logarithm to a coefficient out in front. Okay, so this is kind of the second property of logarithms, and one that turns out to be really, really useful in applications.